Section: Introduction. In this section, we delve into the dynamics of fine-tuned weights under different scenarios. We first look at how changing random seeds affects the fine-tuned weights, revealing that they exist in a thin layer during and after training. We then explore a method similar to model soup, where we average the weights of multiple models. Our results show that averaging weights that are closer together leads to better performance on both in distribution, ID, and out of distribution, OOD, tasks. Based on these insights, we introduce a new approach called model stock, inspired by the concept of chicken stock in cooking. Model stock aims to efficiently merge weights from just a few fine-tuned models by leveraging the geometric properties of the weight space and the anchoring effect of pre-trained models. This method offers a more streamlined and computationally efficient way to enhance model performance compared to the labor-intensive averaging process used in model soup. Our experiments demonstrate that model stock outperforms model soup in terms of computational costs while achieving comparable or even better results. For instance, we achieve an 87.8% ImageNet Top 1 accuracy, ID, and an average of 74.9% on 5 distribution shift benchmarks, OOD, using VIT-L14. This performance is on par with or surpasses existing methods that rely on the clip pre-trained weight, showcasing the practicality and effectiveness of model stock in improving model performance across various tasks. Our study is motivated by two key findings. First, fine-tuned model weights with different random seeds form a thin shell layer-wise in weight space, and second, being closer to the center of this shell is beneficial for model performance on ImageNet and distribution shift benchmarks. These observations lay the foundation for our subsequent discussions on the implications and significance of these findings. Section Summary. In this section, we investigate the dynamics of fine-tuned weights, focusing on how varying random seeds affects weight distribution. We observe that fine-tuned weights with different seeds cluster closely in weight space, and averaging these weights improves model performance on both ImageNet and distribution shift benchmarks. Our proposed method, model stock, efficiently merges weights from a few fine-tuned models, leveraging geometric properties of weight space and pre-trained model anchoring to achieve high performance with lower computational costs compared to existing methods like model soup. Section: Observation 1. Angle and norm consistency among fine-tuned weights. In this section, we investigated the consistency of angle and norm values among fine-tuned weights. Our first observation revealed that the angles and norms of weights from different models fine-tuned on ImageNet were consistent, with very low variations. This consistency was observed across various setups and remained stable during and after training. We found that the norms and angles of these weights showed almost constant values with minimal errors, as illustrated in Fig. This regularity was not limited to a specific model or setting but was consistent across different fine-tuning scenarios. We observed that the distribution of fine-tuned weights had certain properties, such as forming a thin shell around a center point. We approximated the center of weights by averaging differently seeded fine-tuned weights. Moving closer to this center point improved the performance on both in-distribution, ID, and out-of-distribution, OOD, datasets. The distances of fine-tuned weights from the center were highly consistent across different weights, indicating a thin shell distribution. Additionally, we observed that fine-tuned weights tended to occupy local minima edges in the test error landscape. The test error was lowest when weights were close to the center and increased as weights moved away. Fine-tuned models typically resided on the boundary of test error regions, with the lowest error near the center. We also identified a specific weight, W_H, on a line closest to the center, which we will further discuss in subsequent sections. Section Summary. In this section, we observe consistent angle and norm values among fine-tuned weights across various setups and training stages. These consistencies are not limited to specific models, optimizers, or datasets, indicating a general pattern in weight distributions. Additionally, we find that fine-tuned weights closer to the center exhibit improved performance on both in distribution, ID, and out-of-distribution (OOD) datasets, suggesting a thin shell distribution of weights and their proximity to local minima edges in the test error landscape. Section. Observation 4. Randomly perturbed weights nearing the center also merit high performance. In this section, we explored the impact of weights close to the center on model performance. We conducted an experiment where we added noise to the center weight to generate random weights. These random weights showed similar performance to fine-tuned models, emphasizing the importance of being near the center. We questioned why optimization struggles to move weights to the center due to flat local minima. Our hypothesis suggests that fine-tuned weights follow a Gaussian distribution, explaining their geometric patterns. Our method, ModelStock, efficiently merges weights by leveraging pre-trained models to approximate the weight center. By interpolating between pre-trained and fine-tuned models, we can find weights closer to the center. We observed that bias layers rely more on fine-tuned models, while weight layers depend on pre-trained models. Extending this to multiple fine-tuned models, we can move even closer to the weight center. We propose periodic merging during training to continuously approximate the weight center. This approach improves model performance and brings weights closer to the center. Section Summary. In this section, we observe that randomly perturbed weights near the center exhibit high performance, prompting us to investigate the impact of proximity to the center on model performance through a toy experiment. We find that randomly sampled weights show comparable performance to fine-tuned models, suggesting the importance of center proximity. Our hypothesis suggests that fine-tuned weights follow a Gaussian distribution, leading us to propose a cost-efficient weight merging method called ModelStock, leveraging pre-trained model weights to approximate the center of weights more accurately with only a few fine-tuned weights. This method does not require extra training or heuristic hyperparameter settings, simplifying the process and enhancing efficiency. Section. Experiment. In this section, we present the key experimental findings. We begin by outlining our experimental setups. Then, we delve into the main results and ablation studies. For more detailed information, including setups, analysis, and additional results, refer to the appendix. Our codes and weights will be made publicly available. Regarding the models, we tested ClipVit-B32, ClipVit-B16, and ClipVit-L14 models. We fine-tuned two model stock models and compared them with various fine-tuning techniques like model soups, LPFT, CAR-FT, FTP, and FLYP. For ablation studies, we used ClipVit-B32. For datasets, we fine-tuned models using the ImageNet 1K training dataset. We evaluated the model's performance using ImageNet 1K top 1 accuracy for in-distribution (ID) scenarios and considered 5 out-of-distribution (OOD) benchmarks for distribution shift analysis. In our training setup, we initialized classifier weights using CLIP's text encoder and text prompts following model soup. We used AtomW with specific parameters for all experiments. We employed two training setups for comparisons, enabling a balanced assessment of model stock against zero-shot and LP initialized model soups. In the experiments with ClipVit-B32, our model stock showed competitive performance with model soups. Model stock ** even achieved a state-of-the-art performance on ImageNet. Additionally, model stock with WISE-FT demonstrated superior ID OOD performance compared to model soup. Notably, model stock outperformed model soup while using only 2 models, showcasing its efficiency. Moving on to ClipVit-B16, model stock exhibited exceptional performance on ImageNet accuracy and robustness across various distribution shift scenarios. It achieved a state-of-the-art level of top 1 accuracy on ImageNet without relying on additional fine-tuning tricks. In the case of ClipVit-L14, model stock pushed the benchmark scores to new heights with its large-size backbone architecture, achieving state-of-the-art performance on ImageNet. This underscores the effectiveness of model stock across different model scales and benchmark scenarios. Lastly, we conducted ablation studies on ClipVit B32, training vanilla fine-tuned models and model stock for 16 and 8 epochs, respectively, matching the training cost of a single fine-tuning process. Section Summary. In this section, we present our key experimental results. We provide details on our experimental setups, main results, and ablation studies. Our experiments involve fine-tuning ClipVit models on ImageNet 1K dataset, showcasing competitive performance and robustness across various distribution shift scenarios without the need for additional fine-tuning tricks. Section. Experiments on the number of fine-tuned model. In this section, we conducted experiments on the number of fine-tuned models. The table displayed the impact of varying numbers of fine-tuned models on model stock's performance. We observed that as the number of merging models increased, model stock showed improved performance and moved closer to the center. After considering the trade-off between performance and training cost with increased merging models, we found that our setting with 2 models, n equals 2, worked best for model stock. Next, we investigated the merging period of model stock. The table presented results for different merging periods, such as 1,000 and 5,000 iterations. It is important to note that in our experiment, 1 epoch equated to approximately 2,500 iterations. Model stock consistently performed well across various merging periods. We also explored a post-training merging strategy for model stock. We examined an alternative approach where fine-tuned weights were merged only once after each fine-tuning process, similar to model soups. This version was referred to as model stock, post-training. By using individually fine-tuned weights and the same training settings with different random seeds for each model, we evaluated the performance and distance from the center of model stock, post-training, in a table. A comparison was made with a uniform averaging of n models, W_AVG_n, showing that model stock, post-training, achieved improved distribution shift scores with closer distances to the center. Moving on to the discussion, we extended our findings to reinterpret previous studies' mechanics. By building on our insights, we provided a new perspective on 2 key methods, WISE-FT and model soups, to explain their effectiveness. WISE-FT is a robust fine-tuning method for clip-based models that combines weights of pre-trained and fine-tuned models linearly to achieve significant accuracy gains on distribution shifts and ImageNet. We suggested that WISE-FT's superiority over fine-tuned models could be attributed to its weights being closer to the center of the weight distribution, enhancing performance. Model soup merges weights from various fine-tuned models trained with different hyperparameters, leading to improved performance on ImageNet and distribution shifts. We explained the performance enhancements of model soup as a result of weights being closer to the center of the distribution. By interpolating weight vectors from different fine-tuned models, the variance was reduced, potentially contributing to the performance gains. Our findings indicated that proximity to the center of the weight distribution might be more crucial for enhancing performance than the benefits of hyperparameter diversity in weight ensemble methods.